Hey, it's Mike Harrington from YLPCS Mobile Forensics here. I hope you're all doing well and are ready for some great new content on digital forensics topics. As you can see, I'm trying out a new way of doing things, new way of delivering stuff, video. It was a lot of fun to put together, and I hope that it works out and proves useful for you guys. It's definitely something I'm not comfortable with, so I thought I'd try it out. But before I begin talking about today's topic, I'd like to thank everyone for their great comments on the last email series that we put out. It's inspiring to know and that what we're putting out there to the community, people are getting use out of. And just keep those comments coming. Now, like I said in my last series of emails, and just said now, we're working on a new type of course that we're going to be delivering, and video is going to be a big part of that, and releasing information to you. And I'll talk more about that at the end of this video, but I know you want to get right down to it and talk about some digital forensic concepts, so we're going to go ahead and do that right now. So what I'm going to talk to you about today are encoding schemes. And you may ask yourself, what's an encoding scheme? What does that mean, Mike? Well, an encoding scheme is a way that programmers use to encode data as bits and bytes on a storage medium. That same encoding scheme, the same way of storing that, is used in the reverse to translate those bits and bytes back into data like words or images that we as human beings can interact with. So, what does that come into play with mobile forensics? Well, if our forensic tools do not decode it for us, we have to manually reverse engineer data. And this occurs in mobile or digital forensics. And this is one of the greatest challenges to the examiner, is kind of try to figure out what that encoding scheme was used so that we can take that encoding scheme, reverse it, and then figure out what the type of data it is. Fortunately, there are a few common encoding schemes used by programmers that we can identify, decode, and also use as tools to aid in decoding other schemes. So what we're going to do right now is we're going to go look at the common encoding schemes that we have out there. We'll talk a little bit about them using some slides and a PDF that I wrote, and we're going to look at those, and I'll go through them with you to explain them, and then I'll come back and we'll talk a little bit more after that presentation.
Okay, so we just talked about 7-bit GSM encoding. I think it's time to take a little break before we go into bit shifting, which is similar to what we did with GSM 7-bit encoding, and talk about reverse engineering. As much as we would like it to be the case, commercial tools don't always decode everything. They do a great job of decoding the vast majority of the information that you need to make a case when you're doing forensics, but unfortunately there'll be times when you may come across data that you have no idea how it was encoded. You'll have to employ reverse engineering techniques to decode this data. You need at least two things to reverse engineer an unknown encoding scheme. One, you need control data. Text-based strings are the best to use because you can read them, you know what they are. And then a control device of the same make and model of the device you are wishing to examine. You take the control data, you put it on the control device, and you look for the changes that occurred on the control device and see how that they may have changed in order to reverse engineer that. So back to bit shifting. Just to make things a little more interesting, a method called bit shifting can be used to encode or obfuscate data to make it harder to reverse engineer. Bit shifting is a process where bits are shifted left or right by powers of 2 depending on whether or not they're being multiplied or divided. For example, if we take the decimal number equation 2 times 4 equals 8, to get to the product of 8, we multiply 2 by 4, which is the equivalent of multiplying 2 to the second power. Does your head hurt? Because mine hurts. To see how this would work, let's look at the decimal equivalent of the binary equivalent of the decimal number 2. And as you can see here, the binary equivalent of the decimal number 2 is simply a 1 in the 2's place. Okay, now to multiply, we're always shifting the bits left. So if we're multiplying 2 to 4, or 2 to 4, which is 2 to the second power, we're going to shift that bit 2 places to the left to bring it to 8. Okay, so we simply shifted the bit at 2 places to the left to multiply it to the second power and come to the product of 8. Okay, now dividing, we do the exact opposite. We shift the bits to the right. Okay, so let's look at dividing 18 by 2. So here we have the binary equivalent of the decimal number 18. We have a 1 in the 16th place and a 1 in the 2 place. So to divide that by 2, we shift the bits to the right by 2. So we come up with a 1 in the 8th place and a 1 in the 1's place. And 8 plus 1 equals 9. So we're at our correct product. Since we're going to be dealing with hexadecimal data when reverse engineering the dumps that we get from mobile devices, let's decode a 1 byte 8-bit value that has been bit shifted to the right. In other words, it's been divided 2 places. This value, 7F, is what we're going to be looking at. In order to do this, to reverse engineer the bit shifting division, we'll need to multiply or shift the bits to the left 2 places. So we're going to be going the opposite. It's been divided, so now we want to multiply the value 7F 2 places. So we need to shift to the left. So our first step in this is to convert, here's our 7F that we're going to shift over. So the first thing we're going to do is convert the hexadecimal value to its binary equivalent. And here we have the binary equivalent of 7F. The next step that we take is to perform our multiplication. So we're going to be multiplying the bits by 2. So we shift them left. Again, we shift them left 2 places. And here we have them shifted over left 2 places. Okay, you can see as if I go back that we've shifted left 2 places. I'll do that one more time. So the bit at 64 place, the bit here at the 64 places gets moved left 2 places to 256, as you can see right there. But there's a problem here if you haven't noticed it already. Our value just doubled in size. We've gone from an 8-bit value to a 2-bit value. Okay, we only want an 8-bit value though, so where do we go from there? Well, that's pretty easy. To get our 8-bit value, we simply drop everything away from the left of the 8th bit, and we were left with 1 byte. So let's go ahead and do that. Let's drop everything away from the 8th bit, so that's, if we were counting, we'd have 1, 2, 3, 4, 5, 6, 7, 8. So everything to the left of the 128th place, we drop. And here we go. There you go. So the binary value of this 8-bit number is, sorry about that, getting ahead of myself. The value of the 8-bit number here is the hexadecimal FC. That's FC. Right. So let's look at this a different way. Let's prove what we're doing by looking at our standard formula. Okay. So that's what I jumped ahead to. So here we have our hex F 7F again. Okay, so the first thing we do here is you take 7F and we convert it to its decimal value, 127. Since we're going to be bit shifting to the left 2 places, we are multiplying 2 to the 2nd power, or 4. Okay, again, we're multiplying, bit shifting to the left 2 places, so we're multiplying 2 to the 2nd power, which is equivalent to the decimal of 4. Say that a bunch of times if you can. So here's our mathematical equation that we would normally write out. 127 times 4. So we come to the value of 508. Okay? Now, we need to convert this decimal value to hex. This is hex 01FC, and it's a 16-bit number. Okay? So as we see right here. So if you recall, this matches our 16-bit left shifted value that we looked at before. There it is right there, converted into binary. Okay, so 508 decimal equals 01FC. It's a 16-bit value. Now we need to convert that down to the 1 byte. So again, we just drop the 2 leftmost bytes from the 128, and we get left with our value of hex FC. Okay, so there you have it. That's how you do bit shifting.
So there you go. There were some encoding schemes, some reverse engineering. We looked at 7-bit GSM encoding, reverse engineering. We looked at reverse nibbling. And finally, we talked a little bit about bit shifting. And I don't know about you, but my head hurts when I talk about all that kind of math. I'm so grateful a lot of times that the major commercial vendors and and other smarter people than me have been able to do that automatically for us. But like I said earlier, unfortunately, there are times when we're going to need to take that reverse engineering into our own hands and do that. And hopefully that gave you a little bit of groundwork on how to do that. If you like this video and you want to see more of it, please comment down in the comment space below. And if you would also give me a comment on what kind of online training that you like. Do you like it on demand so that you can watch it over and over again? Or do you like it a little more interactive? I'd love to hear your comments. So if you would, please comment in the comment box below. Tell me what you thought of this. Tell me what I can improve. Obviously, I'm not used to being on camera and I trip up a little bit, but I really would appreciate your comments. So I look forward to talking to you the next time. Until then, good luck in all your forensic endeavors.